scalable AutoML approach based on graph neural network. Mossad Helali is a PhD student at Concordia University, going to present that one.
Thank you so much for the introduction. Just testing here. All right, I'm Mossad Helali. I'm a PhD student in Concordia University in Montreal. This is a joint work with Isam and Ibrahim, Julian, and Kavita here from IBM Research. The paper is titled A Scalable AutoML Approach Based on Graph Neural Networks. What is AutoML? AutoML is the problem of automatically generating pipelines, ML pipelines for a given data set. If we look at the AutoML system as a black box, they take a data set, a target column, and maybe the task type, classification, or regression. And the target here is to generate an optimized machine learning pipeline. A machine learning pipeline consists of a set of preprocessors like PCA or normalization or imputation, for example, and an estimator or a learning algorithm like SVM, random forest, logistic regression, etc. So the target of AutoML systems to search over the space of these preprocessors and estimators and the hyperparameters. So the search space is huge. That is, if we do exhaustive search, it will be inefficient because in each of these combinations we need to evaluate this combination over the data set and like observe the target metric like accuracy or a score. Now, if we open this black box to look at the traditional AutoML systems, we will see that AutoML systems are composed of two phases. The first one is an offline phase. It's called meta-learning, or the training phase. And the next phase is the online phase, given a data set, now the generation phase. In the meta-learning phase, the AutoML system, it will collect data sets of different kinds of features, different kinds of properties, number of rows, number of columns, number of numerical, categorical features. Now, and of each of these data sets, it will compute meta features. Meta features are traditionally also statistical-based features like number of rows, number of columns, the mean and the value, number of categorical columns, etc. And now for each of these data sets, we manually look for the best pipeline that optimizes the score on this data set. This is all done offline. Now, when given a new data set, an unseen one, we calculate the meta features for the unseen data set. We compare it with the seen ones to fetch the closest one, maybe by cosine similarity, etc. And then for the associated pipeline of the closest data set, we start looking for the best hyperparameters and the best learners and preprocessors, starting like we start a search space from that point. So, and now we will look for the best hyperparameters and estimators. So the AutoML systems, when they usually try to improve either the meta-learning component or the way to explore the search space. Now, let's have a fresh look at AutoML. This is our work. We named our system KGPIP. Now, let's explore system like data science platforms like Kaggle. You have lots of data sets of different kinds of features, different kinds of domains, and different kinds of properties. And for each of these data sets, you will find the associated machine learning pipelines written usually by experts in these domains. Can we use these combinations of data sets and pipelines in order to develop a meta-learning component? How would that meta-learning component look like? How can we formulate this meta-learning problem as how can we represent it and formulate it? And can we integrate that meta-learning with existing tools for hyperparameter optimization? This is what we propose, and I'll take you through the journey of our system from the pre-processing to modeling and then the generation. Let's begin with the representation, how we represent pipelines and how we represent datasets. First, how we represent pipelines. On Kaggle, you'll find notebooks like this. This is a notebook to read a CSV file, and then it will do train test split, and then a learning algorithm will see. This is a simple pipeline, but you will find it on Kaggle, lots of pipelines like these. And now, a natural representation of this code is actually graphs. So how about if we represent this code as a graph? like by applying static analysis, static code analysis. This is what makes our system scalable, because static analysis can be done instantaneously and applied to lots of scripts on Kaggle. So we use GraphGen for code. This is a tool that is already there by Ibrahim Abdelaziz and others. And this tool applies static analysis, static code analysis on Kaggle notebooks to have pipeline graphs like these. And in these graphs, you will find control flow between statements, data flow between statements, and pointers to external API calls. However, if we take these pipeline graphs as is, it is noisy for the AutoML problem. We need to further filter these graphs in order to have a semantic representation of ML pipelines. So what we do in this work is that we further filter these graphs by focusing on important nodes like calls to ML libraries, scikit-learn, XGBoost, LGBM, etc. These are the libraries used for machine learning usually. And we also filter out statements like printing statements that are irrelevant for machine learning pipelines. Another addition is that we add a node here at the beginning related to the dataset. Adding this node, representing the dataset here, example.csv, adding this node will help link the pipelines that are for the same dataset. So our graph neural network, when it takes these graphs afterwards, it will learn that these pipelines belong to the same dataset. Now, this is how we represented pipelines. How about how we represent datasets? Now, traditionally, we said that meta features are computed by statistical measures. For example, mean, maximum, kurtosis, etc. However, in this work, we learn the meta features. That is, through a neural network, we learn an embedding of columns. We generalize the work by Moller and Smola, where they proposed to learn a column embeddings. Column embeddings are similar like to word embeddings. Instead of like representing the column as is, we represent it with a fixed dense representation. And with these column embeddings, similar columns will have similar embeddings, even if the column values themselves are different, as long as they represent the same concept. For example, if we have two columns of speed in kilometers and speed in miles per hour, they will have similar embeddings. This is the power of neural networks of learning these column embeddings. In this work, we generalize this work of column embeddings by having the dataset embeddings as an average over its individual column embeddings. Now, this is the representation. How about the modeling? Now, we model the machine learning pipelines through a graph neural network, a generational graph neural network. Graph neural networks are neural networks that operate on graphs. A generation model is a model that sees a dataset and tries to imitate it. It's a generation model. This is the first approach to use GNNs in AutoML. And in this work, we adopt a sequential or conditional graph generation. That is, there are two types of generation graph networks, where they generate the graphs as is in one shot, or they generate it node by node or edge by edge. In this work, this is what's called conditional graph generation. So, for example, here, at each step, at each iteration, we figure out whether, or we decide whether we want to add a node or not. And then if we add a node, we decide whether that node should have an edge to an existing node or not. And then if we add an edge, we decide whether like which existing node should that edge be connected to. Like this decide is, all of these three decides are actually through neural networks that are trained using the training set. In this work, we trained our GNN using 11,000 notebooks from Kaggle for 100 different datasets. It's interesting to note here that the generated graphs are not guaranteed to be valid ML pipelines. That is, we apply a validation step for the generated graphs. A graph is valid ML pipeline if it has at least one estimator, like SVM, for example, like a learning algorithm, and that estimator is supported by the hyperparameter optimizer that we are using. That is, for example, in Kaggle, you see lots of techniques, but these techniques are not necessarily supported by the hyperparameter optimizer. All right, now this is the meta learning component. How about the pipeline generation? Now, given unseen data set, how can we generate a pipeline for it? So first, we compute the embeddings of the unseen data set using our column embedding model. Now, and we find the closest data set by embeddings through cosine similarity. This is the closest seen data set. And now we generate a top K ML pipeline skeletons. That is, a skeleton is a pipeline skeleton is an unoptimized machine learning pipelines. It has only the estimator technique and the machine learning algorithm. And then we first insert the node of the closest data set, and then we generate the graph afterwards. We generate the graph on top. And then, like, after we generate the pipeline skeleton, like which does not have the hyperparameters, we supply that to a hyperparameter optimizer, like, for example, AutoScaler or FLAML, and then we return the highest scoring pipeline in terms of the target metric. For example, for regression, we use R-square, and for classification, we use F-score. It's important to note here, like, that generating the K pipeline skeletons is instant. For example, our system could work like, if you want a data set, if you have a data set and you just want to know which technique works better for the data set, generating these techniques is like, or knowing these preprocessor and estimators is instant in our system. All right, how we evaluated our system. All right, we used 4 baselines. AutoScaler, that's the most popular AutoML system, and it's a winner of multiple AutoML competitions. FLAML is a fast and lightweight system proposed by Microsoft in 2021. It also outperforms AutoScaler in some datasets. AL is an approach. It has similarity to ours. It uses dynamic code analysis in order to learn from Kaggle notebooks, but it's not scalable because it only evaluated on 9 datasets because it uses dynamic code analysis. That is, they needed to run these notebooks on Kaggle, which is inefficient, time-consuming. And VolcanoML is a recent system also proposed in VLDB here in 2021. And we have 121 benchmark datasets. This is the most comprehensive benchmark for AutoML benchmark so far. We took the datasets of all these systems and we combined them in order to evaluate our system. Like, for each of these datasets, we evaluate the system and see the target score, and then we average it over the whole datasets. This is a breakdown of where our datasets are sourced from. So we have binary datasets, binary classification, multi-class classification, and regression. And these come from the AutoML benchmark, PMLB, OpenML, and Kaggle. And we consider 2 versions of our system. One, KGPIP FLAML, and KGPIP AutoScaler. That is, we plug in the meta-learning component on these 2 hyperparameter optimizers, AutoScaler and FLAML. All right. As I said, for classification datasets, we use the F-score, and for regression datasets, we use the R-square. This table presents the summary or the average score for all of these systems broken down by the task type. That is, for 77 datasets, this is the average of this system, average F-score of this system on binary classification and multi-classification and regression. And what we see here is that KGPIP manages to improve these systems significantly with a p-value of less than 0.05, not 0.5, 0.05. This is the same also for KGPIP AutoScaler. It also significantly improves the average score over AutoScaler. And basically, we have the state-of-the-art results right now of AutoML. Also, on 44 of the remaining datasets, we compared with VolcanoML, and we also see a significant improvement over the average score. I encourage you to read the paper. It also has more experiments on and ablation studies and experiments on the diversity and the quality of generated pipelines, and also more ways to explore these scores. I realized, like, on 121 datasets, might be a bit difficult to just like average the scores like that. So in summary, KGPIP shows the success of, one, static code analysis as a scalable way to capture the ML pipeline semantics. Second, the learned representation of datasets as meta features. Third, graph neural networks for modeling ML pipelines. The code and datasets are publicly available on GitHub. We designed our system to have like a simple, very simple API. So I encourage you to give it a spin. You can just load the dataset like that and use the simple APIs to fit and predict the score for a simple dataset. Thank you so much for listening. And if you have any questions.
Very nice presentation. So do I understand it correctly that it's mostly about an opening heuristics for finding a couple of skeletons that you can then run the full-fledged kind of model selection hyperparameter tuning? If that is the case, how do I have to interpret those tables that you showed with one score? Because ultimately it's finding good models earlier than a full-fledged AutoML. So where did you have this cutoff point of saying, I give AutoML tools 100 minutes, and that's the average score I'm presenting? So could you maybe elaborate on the variability you've seen in those rates, how you find good models?
Yes, exactly. So like one of the metrics or like one of the parameters of the system, AutoML systems, is the time budget. So that is, when we compare the system, we fix the time budget. Like you can search like the search space, but given this time budget, like you are limited by it. So if you leave AutoML systems for like infinite amount of time, they might arrive to the best pipeline. But you are usually limited by time. So that's why in this study we limited like the systems to 30 minutes only.
30 minutes? Okay.
Yeah, 30 minutes.
Excellent. Thank you very much.
Right. Thank you so much. Yes.
First of all, very nice presentation. So I have one question related to the slide 7. You talk about the graph neural networks, right, to represent the ML pipelines, right? And so are you using graph convolution network, or like are you using graph isomorphism network? So the problem with the graph convolution network is that you can't encode the statistics of the variance much. You only have the statistics of the means maybe, but how large is your graph? So you can represent it with the graph neural network. So two parts of the problem is like, what is the graph neural network you're using, and how large are the graphs are, and why did you choose that?
Yeah. So usually the graphs are something like that. So they are not that big. Maybe like they will have a couple of hundred of nodes maximum. So like modeling that with graph neural networks is like a relatively like straightforward task, and we use this graph convolution network. Yes, exactly.
Okay, thank you.
Thank you so much.
Hi, thank you for the interesting presentation. And this might be a possibly naive question, but can this be like generalized for non-textual data, like image kind of data? Because I think some AutoMLs do handle like the image data as well.
Yes, excellent question. Like our like if you notice that all our datasets, they are actually tabular datasets, and that's why like the most prominent techniques with tabular datasets are not neural network based methods like the SVM or like logistic regression or something like that. They work like very, very successful. But yes, it's actually an extension of our work is to explore how we could benefit from this meta learning technique for like coming up with like good combinations of or like good structures of neural networks. This is what's called neural architecture search. But it's like a future work of ours. Thank you so much.
Thank you.
Thank you.